Welcome everybody. Today is a pleasure to have Suhail Dhawan. Thanks for accepting our invitation. Suhail is a Marie Curie Fellow at the Institute of Astronomy in Cambridge. Before that, he was a postdoc at the Oscar Crane Center in Stockholm, and he did his PhD at the European Southern Observatory in Garching. Suhail worked on the progenitors of the Type 1a supernovae for his PhD. Today, he will present resolving cosmological tensions with Type 1a supernovae. Suhail, you can start, please, when you're ready.
Awesome. Thanks very much, and thanks for the invitation, and thanks for everyone joining to hear about our work. I'm very excited to talk about some of our recent work on using Type 1a supernovae to address cosmological tensions and the path forward with resolving them. So I'm at Cambridge, and the work I've done is in collaboration with the ZTF Cosmo working group, which I was leading for a while during this work, and along with collaborators with the Carnegie Chicago Hubble program. So a brief sort of outline of how I'll go about talking about the different pieces of this analysis. So first, I'll be talking about like a brief motivation. Why is it that we are excited currently to measure both the expansion rate of the universe as well as its directional dependence? And in the first two parts, I'll be looking at Type 1a supernovae for local or near universe measurements. And in the first part, I'll be talking about some recent work I'm very excited about, which is to build a local distance ladder based on Type 1a supernovae from a single survey. So that's the plot on the upper right-hand side. So that's the distribution across the sky of the first data release of Type 1a supernovae from the Zwicky Transient Facility. So notably, this is search and follow-up on the same system. And on the left-hand side, this will be the second part of the talk, is Type 1a supernovae in the strong lensing regime. So this is an independent probe of H0, because here we'll be using time delay distances instead of luminosity distances. So it's a completely independent cosmological observable. And towards the end, so last few minutes, we'll be talking about some recent work that I've been doing along with one of my students and collaborators, so Jess Cowell and Haley McPherson, is on directional dependence of H0. This is something that I'm also very excited about in the context of ZTF and modern low redshift Type 1a supernova surveys. So getting straight into it, and just a brief overview, we have a very well-tested standard model in cosmology. Lambda CDM works very well to explain observations both in the early and the late universe, but it has been known for decades that there are certain theoretical problems like the understanding of the physical mechanism driving both dark energy as well as cold dark matter. So in the search for a more sort of fundamental theory with improved precision in both the statistical and systematic uncertainties, there have been certain recent observational problems that have crept up, and it is important to try and understand what is the origin of these problems. The most significant of which is the observed Hubble tension. So given the audience won't like dwell much on it, just to give like a brief overview, there's a tension at the around 5 sigma level between the inferred value of the Hubble constant using the sound horizon at decoupling as a distance scale in the early universe, assuming the standard lambda CDM scenario and using high redshift Type 1a supernovae and BAOs as guardrails to get what we would call a global or an early universe inferred H0 and the direct measurement from the local distance ladder. Now, this can be pointing towards a very exciting and exotic new physics. Could be early universe changes like additional relativistic species of neutrinos, or some sort of late time physics. I'll talk briefly about that in the coming slides and some recent work that we have done. Or it could be some sort of like new astrophysical systematics that we have not considered. Now, ways in which that we can investigate this is by looking at unaccounted for sources of systematics. And there have been some exquisite works in the literature on looking at what the impact of different systematics would be in the different distance ladders. So typically, like this has been done when calibrating the Type 1a supernova using Cepheid variables. But we also need to have independent distance ladder. So that will be like part one of this talk, which is looking at an independent calibration of the type 1a supernova luminosity using the tip of the red giant branch. So as you can see in the plot out here, this is a plot that people have probably seen quite a lot before. The TRGB value in certain analyses lands right between the value that is from the early universe and the Cepheid distance ladder. And it's important to sort of reduce the systematic uncertainties by having as homogeneous a sample between the different rungs to get to percent level precision. I'll be talking about that in the local distance ladder part of the talk. But also what is important is to have completely independent measurements of the absolute distance scales. This can be either through lens transients, which is something I'll be mentioning in the context of strongly lensed supernovae, as well as like other probes like standard sirens or mega mesas, which are measuring distances that can be completely independent of the distance ladder while still sort of having a strong, precise enough estimation. So since the talk will be centered on type 1a supernovae in both the regime of the distance ladder as well as strong lensing, I wanted to give a brief primer on what really are type 1a supernovae. So type 1a supernovae are a thermonuclear explosion of a carbon-oxygen white dwarf in a binary system. They are extremely bright stellar candles, or like cosmic beacons, because they can be seen at cosmological distances. And while they are not standard, there's a lot of diversity, both in the possible progenitor scenarios, like can they be single degenerate or double degenerate? Are they exploding at the Chandrasekhar mass? Is this just a pure detonation, or is this a detonation to deflagration to detonation transition? So we have a well-observed diversity, but these can be calibrated very well to have a low luminosity dispersion using empirical corrections, and using this were instrumental in the discovery of accelerated expansion and are a very important probe in understanding dark energy today as well. In addition, type 1a supernovae, unlike CoCoLab supernovae, are in all types of galaxies, and that is something that is important when looking at or in having as homogeneous a sample between the different rungs of the distance ladder. So since I've mentioned the distance ladder, and that's the first part of the talk, just a very brief primer on how this measurement is done. So as I'd mentioned, the local value of H0 is inferred by calibrating the luminosity of type 1a supernovae in the nearby Hubble flow, but also with Pantheon Plus and Shoes. This has been pushed to the entire high redshift sample as well. And this is some work that I had done with Dylan Brout and Dan Skolnick and others on sort of combining the left-hand side of the slide with the right-hand side of the slide in order to be able to infer both dark energy properties and the value of H0 simultaneously. Now, in order to do this calibration, we need primary distance indicators. Most commonly used ones are Cepheid variables and the tip of the red giant branch. And as I previously mentioned, in order to do this a measurement very precisely, we need the first, second, and third rungs to be as similar to the next rung as we can have with all of the systematics being minimized. In this, and this is why I am going to be talking in the first part about using ZTF for both the calibrator and the Hubble flow rung of the distance ladder. As I mentioned, we did a combined analysis of the calibrators as well as the nearby Hubble flow along with the high redshift type 1a supernovae. So this has been done in more detail in Pantheon Plus. What we had done was with the original Pantheon, and we got a simultaneous constraint on dark energy and H0. The motivation here was, if we assume that like the error budget is as is given, what kind of the non-standard cosmologies can potentially explain the observed high value of H0 from the local distance ladder. Now, we used a lot of different well-motivated non-standard dark energy models, like modified gravity models, as well as some slow roll dynamical dark energy and thawing quintessence models. In addition, we also saw that the models that include a late time transition in the Hubble parameter were also giving the exact same answer as the fiducial case with lambda CDM. So we didn't see a strong evidence for any transition in the dark energy equation state or the Hubble parameter at a given low redshift, like 0.1 or even lower. In addition, some work that is being led by my student Toby Lovick in Cambridge is also finding that within this covariant analysis, there are no strong deviations seen in the transition in the absolute luminosity of type 1a supernovae themselves, so the capital MB value. So we see that it's interesting that when we take the late time cosmologies, they all seem to suggest a high H0 independent of what their model description is. An independent recent analysis that I did, which I was very excited about for different reasons, which is to look at if we have a perturbation on top of the FRW metric. So if we assume the presence of inhomogeneities and try to constrain it, and we did this within the Dyer-Roeder distance, this is a formalism in which the total matter density contributes to the expansion history, and a fraction of the matter density given by eta times omega matter contributes to the Ricci focusing of the light from the supernovae. This presents very strict constraints on compact object dark matter in the stellar mass range. And what we find is that it is very strongly constrained, like in the most stringent case, up to only 30% in the stellar mass range can come from compact objects. In the more relaxed case, it's around 50% at max. However, what we also see is when we do combine this with all of the distance scale data, we do not find a deviation from the fiducial analysis. So this is the case here in the contour plot, is showing the early universe distance scale only, and adding the BAO and the late time constraints from high redshift type 1a supernovae, we don't find any deviation in the case with the inhomogeneities factored in from the fiducial low value of H0. So even these inhomogeneities would not be a significant part of explaining the observed tension. So that was when we assume that taking the error bars and the measurements as is. Now, what we want to do is also look at, are there independent ways in which we can measure H0, and do these agree with the most precise constraints in the literature, and how can we sort of improve on the precision and therefore sort of get to understanding what can be the cause of this tension. So as I'd mentioned, what I've been working on is type 1a supernovae from the Zwicky Transient Facility. Just a brief primer on what ZTF is. So ZTF is a wide field optical transient facility, which is run out of the Palomar Observatory. It's a successor to IPTF and has a very large 47 square degree field of view. So this means we can scan very large parts of the sky very quickly. So ZTF in its public survey for the first 3 years could scan the entire northern sky once every 3 days in the G and R bands. This also means that we can get a very large yield of type 1a supernovae with well-sampled light curves, therefore to get very good distances in a very short time span, and with a well-understood selection function, because it is an untargeted survey, and therefore you have search and follow-up from the same photometric system. This is extremely important in order to test whether there is any strong environmental bias in the inferred luminosity of type 1a supernovae, as I'll talk about in the next slide. It's also an interesting data set to have new cosmological analyses of type 1a supernovae, like probing the growth of structure, so F sigma 8 at low redshifts, or even to look at anisotropies like directional dependence of H0. And since we want to do homogeneous analysis between the low redshift, the calibrator and the low redshift Hubble flow, this is a single system for both the very nearby supernovae as well as the more distant Hubble flow supernovae. So there is an ongoing debate in the literature about whether or not the Hubble residuals and therefore whether or not the type 1a supernova luminosity depends on host galaxy properties. Now, it has been known for quite some time, more than a decade, that there is a observed mass step in the type 1a supernova Hubble residuals. So the ones after correction in the more massive host galaxies are of order a tenth of a magnitude brighter. Now, there have been more precise studies that have looked at properties beyond just the stellar mass and looking specifically at a local region around the supernova. And there's been a debate about what is the extent to which local properties like specific star formation rate would bias the Hubble residuals. Now, the potential claims that this could be quite high, so up to 5%. And this is important because the scale of the tension is of order 9 to 10%, whereas other studies claim that this is actually a much smaller effect. Now, the untargeted sample of ZTF will be extremely important in order to sample the underlying host distribution. In our DR1 paper, what we saw was that we already observed a sample of 761 type 1e supernovae. For context, at that time, the low redshift sample was only a couple of hundred type 1e supernovae from all other samples put together. And this is extremely important because, as we can see here, there's a large number of supernova host galaxies in the low mass regime that were previously being missed, that with the untargeted search and follow-up with ZTF, we can now find a very large number of these host galaxies that are in the below 10 to the 10 stellar, 10 to the 10 solar mass category. And this is extremely important in order to test whether or not there is an environmental bias with a large sample of homogeneously measured type 1as. So what we need beyond just the type 1e supernovae, as I previously mentioned, is to calibrate the luminosity using primary distance indicators. Now, since ZTF is untargeted, we find that we also get a large number of type 1as in the high and low mass host galaxies. And what we wanted to test was using a distance indicator like the tip of the red giant branch, which can measure distances in the high mass host galaxies or in the older stellar populations as well, to see whether or not that value would agree with the local estimate from the Cepheid calibrated distance ladder. As we can see here, so this is a plot from recent HST proposal that the calibrators in the TRGB sample matched the host galaxy distribution very well of the ZTF year 1 sample compared to, for example, the bias sample from the literature, which only looks at a particular kind of host galaxy type. This is also important because the TRGB is a distance measure that is in the outer halos of galaxies. So we can test things like whether or not the impact of crowding and blending or extinction is something that is causing any sort of strong systematic shifts. This has been tested in the literature with Cepheid calibrators. The aim here was to test it with independent distance measurements. So the ZTF sample is also ideal because, as we can see here, compared to what the state of the art with DR1, the median host redshift is twice as high. So there's less systematics from peculiar velocity uncertainties. And from the light curve discovery, as I had mentioned, because the survey looks at large parts of the sky and discovers supernovae very early. The ZTF sample discovers the supernovae a lot earlier than the current literature sample. This is particularly important because the standard model, the GET distances, uses the width luminosity correction from the declining part of the light curve. But it is known both from supernova models, but also empirically, that the rising part of the light curve offers a lot more information to further standardize them and improve the scatter in the distances. This is something that wasn't possible to do with a literature sample that was very heterogeneous and not with a significant amount of early data, and something that we can improve upon with ZTF quite significantly. And this is the aim with a more finalized cosmological analysis with the second data release. So as I've mentioned, we have a Hubble flow sample that is around 700 type 1a supernovae in a small volume that's about 300. And we also need calibrators. And what we wanted to do, so this is the study from earlier last year. We looked at how many of the calibrator type 1a supernovae, which is within a small nearby volume of 20 megaparsec, actually have HST data. We looked at what would be the impact of sample selection, so looking at different redshift cuts for the Hubble flow, as well as the light curve fitter. And we find that that is a significantly sub-sigma impact. And looking at this entire sample, we then calibrated it with the archival data for a single type 1a supernova, which had HST data already. And what we find is that we get an H0 that is like consistent. So with a single calibrator, we wouldn't be weighing in on the tension, but this the estimate of H0 is consistent in the error estimation with like the current best sample of calibrators. So with each individual object that we see in the literature large sample analyses, the errors are approximately the same as what we get for the single ZTF only distance ladder. What we also see is that the calibrator sample is extremely well sampled as well. So it allows us to improve distances both in the Hubble flow as well as for these nearby objects, such that we can further reduce the scatter and the final uncertainty on H0. There's a lot of these improvements that currently are sub-sigma because we have a large uncertainty from just a single calibrator. But our outlook is that with JWST now functioning in cycle 2, we have a proposal to get distances to nearby ZTF type 1As that are in elliptical galaxies only. And this is important so that we can actually have an independent test of environmental systematics. So essentially saying that if the ellipticals H0 agrees really well with what we get from Cepheid host galaxies, this would be a very strong piece of evidence suggesting that this is pointing towards new cosmology. Now, we also have an augmented Hubble flow sample. So as I'd mentioned that in DR1, we have about 750 type 1As. ZTF DR2, which stay tuned for in this year, will be around 3000 type 1A supernovae. And this is going to be an extremely large Hubble flow sample to do both H0 studies, but also to look at anisotropies and sort of move beyond assuming FRW when we're doing an estimation of H0. So this is very exciting because it is taking essentially just one telescope for the calibrators to get distances with the TRGV, and using just one telescope for the supernovae in order to get the Hubble flow in the calibrators, such that we can then reduce this uncertainty, which is currently at the 8% level, to something that is at the 1.5% level. So this is something that's very exciting on the distance scale. I'll pause for a bit for questions before I move on to the part about strong lensing.
Just if I can jump in, there are flows, anomalous flows in the local universe, right? So we know there's a flow towards Shapley, right? This work of Brent Tully and collaborators, and there is belief that this continues beyond because you see anomalies in scaling relations in galaxy clusters. So, I mean, this looks like a great study. It looks like you really are going to find something. You're going to find an anisotropy in these supernovae samples once you have good enough sky coverage. And we have like preliminary results that are already showing that those effects are there. Adam has a comment, but it's just unrelated from the last paper, Adam. We can discuss that elsewhere.
Sorry, so I think that's unless before the other questions. I think that's
I had a question.
Yes.
So I don't think I've seen any TRGB distances much beyond 20, 25 megaparsecs. So how do you know that you can measure TRGB all the way out to 80 megaparsecs?
Right. So that's
maybe you could deal my question and Adam's question, right?
Awesome. So okay, that's a great question. So the feasibility of HST is definitely a lot more limited than for Cepheids, and this was sort of taking a very sort of approximate tip estimation and seeing what we can get from like cycle 1 and like from the GTO data, like how well can NeoCam do, how deep can it go, and like at what point can it resolve the stars. 80 might be the absolute outer limit, but it's quite feasible even like at 60 to 70 megaparsec. But I totally agree that like we would need to actually get like, so all right, so my point here is that we have the supernovae already in those host galaxies, and we have them like without sort of selection bias, so we have them in ellipticals and spirals. It does remain to be seen how far we can push it. This was using like an approximation based on like how well NeoCam is performing currently. So that's to sort of explain that number.
And also, I'm sorry, but are you saying you have 106 type 1a supernovae in elliptical galaxies within,
sorry,
you know, what is this, redshift 0.02?
So this is 106 ellipticals and spirals. The elliptical sample is about the same fraction, about like 40-45% of these. So we started with a small proposal of like 10, and the aim is that to sort of build it up. But if like the ellipticals agree with the spirals, then we would like have the entire sample in the volume limit, so that we can push down to the uncertainties that we sort of need, you know, in order to have a completely independent JWST ZTF distance ladder.
Right. Can I ask how many supernovae you would have below 500 megaparsecs?
So,
and whether or not would you have good enough sky coverage to see this anisotropy we expect?
Yeah. So
based on other results.
Excellent. So I was going to get in my head, I always go from calibrators to Hubble flow. That's just how it's tuned, but yes. So it's definitely interesting, and people are looking into the different redshift shells and seeing whether or not we have any signature for dipole that points towards Shapley. So there's a few hundred supernovae in the redshift shell, like 0.035 to 0.055, which effectively includes like the entire extent of the Shapley supercluster. And so within sort of 500 megaparsec, we should already have like around 2000 spectroscopically confirmed type 1As approximately. Maybe it's closer to 1500. I haven't, at 0.01, at 0.1, it's around 3000. At around 0.06, it's around 700. So at 500 megaparsec should be somewhere between those two.
Sound like very good numbers then.
Yeah, and they're all sky. So like it's not like targeted follow-up. So so you won't have like aliasing issues when you're trying to model the selection effects for anisotropies.
All right, thanks.
Sweet. Awesome. So thanks for that great discussion. And the second part of what I'll be talking about is on an independent way in which type 1As can probe H0, and this is through strong gravitational lensing. Now, the idea for strong gravitational lensing to measure H0 was originally proposed for supernovae by Schur-Refstal in 1964. So as you can see, in a favorable alignment of the source observer and an intermediate deflector, we can get multiple images of the background source. And if that source is transient, we can actually use features in the light curve in order to measure time delays. And along with measuring the thermal potential of the galaxy and line of sight structure, we can get accurate estimate of H0, as is shown in this equation at the bottom right. Now, this has been done with strongly lensed quasars, but strongly lensed supernovae, while rarer, have certain advantages. Like we need a lot less monitoring. We see that the supernova light curves are typically just these single bumps with a couple of weeks rise time and then declining onto an exponential tail, compared to the long time scale that we need to monitor stochastic light curves of quasars. Additionally, because of their standardizable luminosity, this is some work done with Simon Vera, where we were looking at how many supernovae we would need in order to break modeling degeneracies, like the Marsh-sheet transformation. And there's also evidence from the literature that there's lower impact of microlensing systematics. And because supernovae actually fade away, we can get the host plus lens. So without needing high contrast imaging with the source, we can actually confirm the lens model after the supernova has faded beyond detectability. So the other very exciting thing about lens supernovae, specifically of type 1a, is that because the type 1as have a standardizable luminosity, they can be discovered without needing multiple imaging. So on the left-hand side, this is the discovery image of IPTF 16GU. It's a bit of a mouthful, but like super exciting event that was detected in 2016 by the predecessor of ZTF, the Intermediate Palomar Transient Factory. And this was detected essentially because a supernova that was around 18.5 magnitude at peak, when the spectrum was taken, was consistent with a redshift of 0.4, which was already like sort of alarm bell that something is very interesting, because at that redshift for the given apparent magnitude, it was corresponding to an event that is around 50 times brighter than a normal type 1e supernova. Now that made it a huge outlier, and we immediately sort of triggered HST follow-up. And with that follow-up, we can actually resolve the individual images. This was also done with adaptive optics from the ground. And as I was mentioning previously, we can actually get a template afterwards. That's important both for the lens modeling, but also to get accurate photometry, because you can get a difference image on which we can with which we can build these light curves and multiple filters. Now, unfortunately, this is an extremely bright event due to the high magnification, and that is combined with the fact that it is very symmetric. So because it's very symmetric, the time delays are very small, of order a day or less between the 4 images. And given that the coverage began a lot after peak, the uncertainties are too high to do a direct H0 inference. But there's a lot of complementary science that's very exciting with the lens supernova system. So as I'd mentioned, like, it's a symmetric system, small time delays. So the model prediction for flux ratios was very close to being 1. But this plot, which shows the individual image magnification, shows that image 1 is extremely highly magnified compared to images 3 and 4. And what we did was, using the multi-filter HST photometry, we can actually constrain extinction in the lens in each individual line of sight. And using these constraints, we can actually get both the color excess as well as the slope of the dust law in that individual line of sight in the lens galaxy. Now, that's something that's very important, because taking that extinction into account, we can measure the lensing magnification very precisely. And this is measured with a very small uncertainty compared to what we would get without the multi-filter coverage, because therein they would suppress the inferred extinction to close to 50. So it was systematically offset on an amplification distribution. So it's extremely important to get these multiple filters such that we can constrain the amplification in a model independent way. And we can also, in this particular case, use the fact that there is a possibility of microlensing magnifying one of the images to study the stellar network, and possibly also look at independent constraints or like exotic compact objects, and whether or not they would explain the flux ratio. So this is something that has been seen for lens quasars, but can be done with lens supernovae by having more accurate flux ratio estimates from using the fact that the luminosity is standardizable. So there's a lot of interesting science that we could get from like the extinction in lines of sight, as well as a model-independent lensing magnification estimate. So after much sort of searching with the Zwicky Transient Facility, which was the follow-up to IPTF, late last year, or like in fall last year, we discovered the first lens type 1e supernova in ZTF. So as you can see, it is not resolved in the ZTF images, but even when we use a higher resolution follow-up with the VLT, while we could like decipher the lens redshift and get a higher spectral resolution as well in order to study the supernova in detail, we could not resolve the multiple images, still a follow-up observation with Keck in the J band. So again, as with Zwicky, this is an extremely symmetric system, so the time delays were extremely small, and we can see that also in the unresolved data. So this is data in multiple filters, G through to Z from the Liverpool telescope. And that was particularly important in order to also constrain the extinction. We can see that this essentially looks like just 2 overlaid images of a type 1e supernova without any time delay. So this could just as well be fitted with a single type 1e supernova with a magnification without needing a time shift. And that is the inference that was done in Ariel's paper as well. And we are using this also as a gravitational telescope in order to get more follow-up spectroscopy, because the lensing magnification makes the supernova bright enough such that we can get very high signal to noise spectroscopy at redshift 0.35. So it's a look back time of 4 billion years, at which we can actually study the spectral evolution of the supernova itself, and comparing it to low redshift supernovae, look for whether or not there are subtle differences in the spectroscopic properties and how that would fold in to systematic uncertainties for like dark energy studies with intermediate to high redshift supernovae. An additional sort of thing that is very exciting because of JWST now being available is that we can actually study the inner core of this supernova at extremely, like at intermediate redshift and at redshifts that are a lot higher than where we have been able to do nebular spectroscopy. This is important to study the progenitor system because it tells us a lot about the central engine that is driving the type 1e supernova. So it's something that's only really possible because we have 3.5 magnitudes of magnification from the strong lensing. So this was with the current set of surveys, and as we see that we only have like a small handful of supernovae that also a small sample of lens supernovae and an even smaller sample of lens type 1e supernovae. So what we wanted to see was, with the deluge of data that is expected with the Rubin Observatory's legacy survey of space and time, will we be able to have the data in order to do a precise H0 measurement with lens supernovae? So the study I alluded to with Simon Bera, we looked at a hierarchical Bayesian estimate of the number of supernovae that we require in order to get to percent level with LSST data. And so what we found was that a few tens of lens supernovae are good to get to that required precision, such that we can be competitive with local distance ladder estimates. And also some work that I'm doing with Nikki Arense in Stockholm is using a realistic cadence, seeing will we actually be able to find this in the LSST observing strategy, and which observing strategy would be the best, and how can we like allocate resources in order to be able to get the optimal constraints on time delays and therefore on H0. What we find is that the number that we need for about 1.5% can be found in a few years of operation. So after like the first season of reference building, in a few years, we'll be able to get the sample that is required in order to reduce the uncertainties from the total sample to at 1 to 1.5% precision. I'm also working on the combination of ground and space-based data like we did for 16 GEU, and seeing what is the most robust way to trigger follow-up such that we can reduce the uncertainties on the time delay and get an accurate estimate of 6 to 7% per object on H0 from lens supernovae. So there's a lot of exciting work in LSST, would be an excellent discovery machine, but along with resolved follow-up in order to get the precision that we need for measuring time delay distances accurately. So in the last part, which is just a few minutes, I'll be talking a little bit about some recent work that we've been doing on constraining directional dependence of the expansion rate. So far, all of the analyses on H0 have assumed isotropy or an FRW metric when doing these constraints. But is there some suggestion that we can actually constrain H0 as a function of the direction of the sky, and whether or not that can tell us something about either local large-scale structure or potentially exotic early universe theories? Now, the reason why this is exciting is because now we actually have surveys, like I mentioned with ZTF, but also like with the cross calibration of different surveys in Pantheon Plus, where we can start to test the constraints on the luminosity distance as a function of the direction on the sky. So this is the sort of generalized cosmographic expansion. So in the FRW case, this would just be Q0 and H0, whereas here we're constraining H and Q as a function of the direction. So this was work that was done both by me and a student, Jess Cowell, who's now at Oxford. And what we saw was that from numerical simulations, the expected highest amplitude multiple in the deceleration parameter would be the dipole, but in the Hubble parameter would be the quadrupole. And this can be constrained with the newest data sets quite precisely. And given the fact that there's like a claimed sort of tension between sort of different estimations of the dipole, we wanted to see what we can actually find with complementary constraints on the Hubble quadrupole. So what we see here is that on the left-hand side, this is constraints on the quadrupole. What we find that like with the Pantheon Plus sample, if we use different sort of exponentially decaying scales of the quadrupole, we see slight deviations from isotropy in this case, but we still need to sort of cross-check this against like homogeneous samples that have a well-understood survey selection function. We also find that like even if we use different cases for exponential decay, they don't shift the monopole of the Hubble parameter from the isotropic case by much. So it doesn't, again, like affect the tension very significantly. The changes are sub kilometer per second per megaparsec. But with the ZTF sample, as I mentioned, we already have a DR1 sample of 700 type 1e supernovae across the sky. But with DR2, we're going to see like an extremely large low redshift sample of around 3000 type 1e supernovae. And in our paper, we did some forecasts seeing that if the constraints as they are right now, so if that was the true value of the quadrupole, with the systematic and statistical uncertainty budget, will we be able to actually distinguish that from an isotropic case? And the thing that we are quite excited about, even though it is still like in the forecast domain, is that we can actually at a 6 sigma level test whether or not this anisotropy is truly there when we have a sample as big as ZTF. So currently we're working on sort of working in the systematics into a full forward simulation such that we can actually get these constraints out from the DR2 sample. So very excited about this, and this is something that like moves away from just assuming FRW, but something that we can actually do in the near term. So I'll leave my conclusions up here, and I thank you all for your attention and very happy to take questions and discuss more.
Thank you so much. Thank you for the nice talk. Do you have any questions? Yes, Shaheen?
Thank you for the very nice talk. I have a question regarding this last few slides on the anisotropy. Can you explain why we don't expect to have a dipole on the H0, but only on the acceleration?
So I think if you look at the divergence of the scale factor in these simulations, it basically means that like the second order term, which is the dipole, goes to 0. The maths in like is in a paper that we've referred to, which is by Asta Heinesen, who is one of the co-authors. So they basically evolve the scale factor in without assuming FRW, and then look at what the divergence would be, and the second order term in case of the Hubble parameter goes to 0. I should maybe like offline I'll point the exact math as to why that disappears, and we see that in the numerical simulations as well. So you see that if you look at like a power spectrum analysis and just look at the CLs in the Hubble parameter, apart from the monopole, the one that's the largest is the quadrupole, and that's in Jess's paper. I can point you to like looking at that power spectrum analysis.
Okay, thanks. But to me, this would mean that you're basically taking the data in a very particular frame, not a CMB frame, some other particular frame where you can remove the dipole in the H0. And the question was what that particular frame is.
Right. So I think so. There's two things there. Decoupling them about the frame. So this is with the peculiar velocities added in. We don't find that if we just take the CMB frame without the peculiar velocities, we don't find that changes the value of λ1 significantly. Like it moves, I mean, it's only a 2 sigma sort of deviation, so it just moves it slightly. So we don't find that the frame makes a big impact on the quadrupole. It does on the dipole of the deceleration parameter. But what I was saying was that that's actually from the models itself. We find that the power of the dipole in H0. So it's not because of what redshift we use. That's just purely from the numerical models that we find that the dipole should have a much smaller power by like a few orders of magnitude compared to the quadrupole.
Okay, so I'll take a look at your paper and will bother you with questions through email.
Yeah, sounds awesome.
Thanks. Thanks.
Thank you. We have a question in the chat. I don't know if you can.
Yeah.
Chat.
So that's an excellent question because I've been working on the ZTF siblings to the point that we had a really nice telecon this morning itself. So we've kind of finalized the sample. It's a very nice coincidence. So ZTF, in its sort of 3 to 4 years of phase 1 of observations, has already gotten around 20 to 25 siblings. So spectroscopic 1As in the same host galaxies, spectroscopically classified ones. And that is definitely important. And what we're doing now is like looking at sort of the systematics that fall off in common, like global host galaxy properties and peculiar velocity uncertainties, and actually sort of constraining things like the alpha parameter, which is the slope of the width luminosity relation, and the beta parameter, the color luminosity relation slope, and trying to understand what the diversity is and how that tells us about like the intrinsic dispersion of supernovae. So things like not only getting alpha and beta, but also is the X1C distribution as similar to the non-siblings, and like is the intrinsic scatter the same, and like are the pairwise distances more precise. So that's some ongoing work, and we have a pretty large sample to do that.
Thank you. Adam has another question.
Sorry, I was just going to follow up on that and ask, do you get unique information from the siblings that you don't get from the Hubble flow? It just seems like you have such a bigger sample in the Hubble flow, and of course you have redshift to give you a relative distance. So how is that going to help?
That's a good point. So if we split that into the two sources systematics, the thing that we get from siblings is that the global host galaxy properties are in common. So we can actually compare that to an entire random sample where the properties are not in common, and just see, are the pairwise correlations and distance estimates better for siblings compared to like non-siblings. But what we can do, and rightly so, like with a large sample like that, we could just make like redshift siblings, which is just like taking a small slice of redshift near the median and considering all of them as like being, you know, kind of at the same distance, so we can get like a distance independent way of constraining like the standardization parameters. That's something that we independently wanted to try as well. But with the siblings, the benefit is then we can actually do stuff with local properties. So like seeing whether they're different based on like a locally inferred color or specific star formation rate. That's something we can't really do with objects that are in different host galaxies. So that's the benefit of the sibling sample. But if we're just looking at like reducing peculiar velocity uncertainties, we can do what you're suggesting with like redshift siblings.
Thank you. And do you have any other questions, comments? No, so I think we can thank Suhail again. Thank you so much.